In this problem, we're given the language infinite DFA, which is defined as the set of the encodings of M, where M is a DFA and the language of M is infinite. We are asked to prove that this language is decidable. So first, let's define a few of the things in this problem. Firstly, again, infinite DFA is a language, so it is just a set of strings. By definition, in the language of infinite DFA, M is a DFA. And M inside of these angle brackets is the encoding of M. An encoding of M is simply a string representation of the DFA M. So I tend to think of this as the actual formal specification of the machine. When we write out this 5 tuple and the specification for each of these items in that tuple, we are writing out a string encoding of the DFA. So that's what I imagine for the encoding of M, but this could be any encoding of it, including, say, a binary encoding, which is what we tend to think of in Turing machines, in computers. The language of M is, again, just a set of strings. And we're asked to prove that infinite DFA is decidable, which means that there exists a decider for the Turing machine that decides the language. Or I'm sorry, there exists a Turing machine that decides the language. This Turing machine is said to be a decider if that Turing machine is given some input and it halts and accepts if that input is an element in the language, or it halts and rejects on the input if the input is not an element in the language. But no matter what, the Turing machine will halt. Now, you may be wondering, if we have to create a Turing machine that decides this, do we have to write out a formal definition of the Turing machine to prove that it's possible? And the answer is no, for this reason. Turing showed us that an algorithm is any method, idea, or procedure that can be implemented on a Turing machine. Or any attempts, really, that we've seen to define an algorithm has been shown to be equivalent to Turing machines. So, so far it seems like the definition of an algorithm is equivalent to the definition of a Turing machine. This is very useful because that means all we have to do is come up with a series of steps that proves that we can solve this problem, and we know that we can then create a Turing machine that will do the same thing. Now, in order to tackle this, we're going to need a few tools. To start, I'm going to create yet another decider. And it's going to be the decider for the language of E DFA. I'm going to tell you that, well, E DFA, which is the set of strings that are the encodings of M, such that M is a DFA, and the language of M is the empty set. I'm going to tell you that this is decidable, which you shouldn't believe unless I can prove to you that I can create a Turing machine that decides this language. Well, doing that is actually fairly simple. Imagine that we're given any DFA. How do we know, how can we tell if that DFA recognizes at least one string, if it'll accept at least one string? Well, we know that we'll be given a set of final states. That set could be empty, but even if there's a final state in the set, it's possible that it might not actually be it might not be possible to get to that final state from the start state. So really, we want to check to see if there is a path from the start state of the DFA to a final state. There could be more than one. if a path exists from the start state of the DFA to the final state, then this DFA will accept at least one string. If it accepts at least one string, then certainly the language of the DFA can't equal the empty set, which means that our Turing machine that decides E DFA should reject. Otherwise, if there is no path from the start state to the final state, then this DFA can't possibly accept any string, which means the language of the DFA is the empty set. Therefore, our decider should accept. So we've now proven that we can create a decider for E DFA, which will tell us, given the encoding of any DFA, if that DFA is in this language or not. This will prove to be useful very soon. Now, looking back at our original problem, we're asked to prove that if given the encoding of a DFA, if the language of that DFA is infinite. So now we should be asking ourselves, well, is there some procedure that we can follow given any DFA to determine if the language of that DFA is infinite or not? Well, by now we kind of have a general idea of how we can tell if a DFA can generate or can accept an infinite number of strings, right? So let's look at an example. If we're given this simple DFA, clearly the language of this DFA isn't infinite, because the language of this DFA is only the strings 0 and 1. So what would we need in this DFA in order for it to recognize an infinite number? Well, if we had a similar one, but this had a loop somewhere on a path between the start state and the final state, then the language of this new DFA would clearly be infinite, because we'd see that this DFA would accept the strings 0 and 0, 0 and 0, 0 and 1, 0, 1 and 1, 0, 0, 0, 0, and it could keep taking this loop. So if a loop exists from our start state to our final state, we can see that the language of the DFA will be infinite. Well, what's the longest string that could be recognized by a DFA that wasn't part of a loop? The best case scenario here seems like, well, if a DFA has a finite amount of states, which it must, then the longest string that could be created by a DFA where all of this, where its computation went through every state, say like this, then the longest string that could be accepted by this DFA that didn't go through a loop in its computation would be of length 2, right? Because it would just go through these two. And in order for a string to be of length 3, it would have to have gone through this self loop. And this is kind of the best case scenario. Like, it's touching every possible state. And even if it goes through every state in the DFA, once it once it's hit all of them, in order to recognize a string of a longer length, it's going to have to return to one of those previous states. So certainly then, if we had a different DFA that had 5 states, we could also certainly say that in order to have a string of length 5 or more, it would still then have to have gone through a loop. So we can count the total number of states in any DFA, and in order for a string to be at least as long as that number, it would have to have gone through a loop in its computation. This brings us to something that we're already familiar with, called the pumping lemma for regular languages. The pumping lemma states this, that if a language, which we'll call L, is regular, then there exists a pumping constant, P, such that for W is an element in the language, for all W whose length is at least P, then we can decompose W into 3 strings, X, Y, and Z, such that the following hold. The length of XY is less than or equal to P. The length of Y is strictly greater than 0. And xy to the iz must be an element in the language as well for all I greater than or equal to 0. So previously we've used the pumping lemma for regular languages to prove that a language wasn't regular, because we know that every language that is regular must follow these set of rules. So if we could prove that it didn't follow this set of rules, then we could prove that it wasn't regular. We also said that proving that a language did follow the pumping lemma didn't prove that it was regular, so it was necessary. Pumping lemma is necessary for a regular language, but it's not sufficient. And this is pretty obvious because we know that context-free languages also use a pumping lemma, and just because a language is context-free doesn't mean it's regular. But in the context of this problem, we're told that we're given the encoding of a DFA. And if we have a DFA, we know the language of that DFA is regular. So we know then that this pumping constant P must exist for the language. And in fact, that's what we were getting at up here. We showed that for any DFA, we could simply count the number of states in that DFA, and any string with at least that length had to be generated by a loop, which means that we could just set the pumping constant P to the number of states that exist in the DFA. And in that case, if we have a string whose length is at least P, then, well, we know that the length of Y has to be at least 0, strictly greater than 0, I should say, and xy to the iz then is going to be an element in L for all greater than or equal to 0. So for I equals 0, we'll know that xz is an element in the language. For I equals 1, xyz is in the language. For I equals 2, xyyz is in the language. So for this infinite number of I, we can see that there's an infinite number of strings that will be in the language. the moment that we see a string of length at least p, there's also an infinite number of other strings in the language. So this is useful. We've just shown that the moment a language has a string of length at least p, where p is set to the number of states in the DFA, then the language must be infinite. So how can we use this? I'm going to give you a hint here. If we took some language L, and we removed from that language all of the strings that weren't of length at least p, if we were left with more strings, if we weren't left with the empty set, so there were more strings in that language, then we'd know that there was a string in the language of length w, or of length p, which means that there also has to be an infinite number of strings. On the other hand, if we removed from the language all of the strings of length whose length wasn't at least p, and we were left with the empty set, then there would be no strings of this length, and we would prove that the language wasn't infinite. So we can use E DFA, the decider for E DFA, to do just that. If we're able to come up with an encoding of a DFA that is the initial language minus all of the strings that aren't of length at least p, and that language is the empty set, then we'll be able to show that the language is infinite. If it is the empty set, then the language can't possibly be infinite. Well, this means that we're going to have to come up with this new modified DFA that only contains the strings of length at least p. So let's prove really quickly that we can do that. I'll call it m at least p, and let's say that p was the value, the constant value 3. Well, certainly I could create a DFA like this. And if the alphabet of the language L was 0 and 1, then we would do this over the same alphabet. And here I've shown that very simply I've created a DFA that will recognize all strings of length at least 3. Well, if the value of p was 4, I could fairly arbitrarily just add in another state here, and now we have a DFA that recognizes all of the strings of length at least 4. So no matter what constant integer value p we're given, we can certainly create a DFA that recognizes all of the strings of at least that length. Well, now we need a DFA whose language is the language of L minus all of the strings who aren't at least this length, and we can do that very simply by simply saying, well, let's say L equals the language of how do we want to say this? Yeah, let's say L equals the language of M, then the language of M intersected with the language of M at least P is going to be the language of all of the strings in the language of M whose length is at least the length of P. We know that regular languages are closed under intersection, which means we also know we could create a DFA that accepted the strings in this language. So we could then take the encoding of that DFA and pass it into E DFA, and it would do what we wanted, which will bring us now back to the problem at hand, where we are asked to prove that the language infinite DFA is decidable. We said all we needed to do was to come up with an algorithm that could decide this language. If we can come up with an algorithm that does it, we can create a Turing machine that does the same. So, what do we want to call the decider for infinite DFA? Let's call this DFA is going to be the decider, the Turing machine that decides this language. And it'll be defined as the following. Given the encoding of M, where M is a DFA. Well, we said the first thing that we wanted to do was determine a value for P. That was going to be important. And how could we set a value for P given any DFA? Well, we could simply count the number of states in the encoding of that DFA. So we'll count number of states in M and set P to that value. So P equals the number of states in M. Next, we wanted to create a new DFA, which we'll call A, over the alphabet of M that accepts all strings of length at least P. Now we want to create another DFA which we'll call I, that accepts the language that is the intersection of the language of M with the language of A. Now, if we run E DFA, on the encoding of I, if E DFA accepts, that means that after removing all of the strings from the language of M that weren't of length at least P, that we were left with the empty set. If we were left with the empty set, then the language of M couldn't be infinite. So our decider, D DFA, should reject. If, on the other hand, E DFA rejects, then we know that there's a string in the language of M that's at least the length of P, which we've shown could only possibly happen if there was a loop in the DFA. And we know from the pumping lemma that if there's a loop between the start state and the final state, then the DFA can accept an infinite number of strings, so the language of that DFA is infinite, and therefore D DFA should accept. And this concludes the proof that infinite DFA is decidable because we've just created a Turing machine that decides the language. Given any input, it will either accept or reject. Now, let's look at a similar problem. Before it was for infinite DFA. What about a new problem, which we'll say is to prove that 3 DFA, which I'll define as the encoding of M such that M is a DFA and the language of M contains at least 3 strings, is decidable as well. Well, if we were given a DFA, the state diagram of a DFA, could we look at that and determine if there were at least 3 strings in the language. Which cases would need to be covered? Well, when we looked at E DFA, we said that if a path existed from the start state to the final state, then the language has to consist of at least 1 string. Well, we can use that same logic here and say that if there's a path from the start state to the final state, then there certainly has to be at least 1 string in the language, because it's going to be the string accepted when those transitions were taken. Well, if there's 2 paths from the start state to the final state, then using the same logic, there's at least 2 strings in the language. And if there are 3 paths from the start state to the final state, then there have to be at least 3 strings in the language. But that doesn't cover every case. It's possible for us to have only a single path like this in a DFA and still have at least 3 strings. Well, how is that possible? We just showed it on the previous problem, which is that if there's a path from a start state to a final state, and that path goes through a loop, then the language of the DFA is infinite, which means the language of the DFA certainly contains at least 3 strings, because it contains an infinite number. So if we can come up with an algorithm that checks these 2 cases, we can then prove that we can create a Turing machine that decides 3 DFA. So let's do that. Given an encoding M, where again M is a DFA, first thing that we'd want to do is find all paths from the start state to the final state. Now we know that we can do this and do it in a finite amount of time, because DFAs have a finite amount of states and a finite amount of transitions. And we know that there are several different algorithms we can use for pathfinding if we were to treat a DFA as a directed graph, where the nodes of the directed graph were the states and the edges of the directed graph were the transitions. Then we could use depth first search, breadth first search, Dijkstra's, Ford-Fulkerson. We have all of these ways of finding paths. And in this case, we wouldn't want to find just the shortest path. We would want to enumerate all of the paths. Since there's a discrete amount that we could possibly have, we could certainly enumerate them. So if we find all of the paths from the start state to the final state, if there are at least 3 paths, our Turing machine that's deciding this language should automatically accept, because then we know that there are certainly at least 3 strings in the language. If there aren't at least 3 paths from the start state to the final state, then we could run the decider for infinite DFA on the encoding of M. And this will cover the other case for us, where if the decider for infinite DFA accepts, then we know the language of M is infinite, and therefore our decider for 3 DFA should also accept, because that means that the machine being encoded has at least 3 strings in the language that it accepts. Similarly, if the decider for infinite DFA rejects, then the language is not infinite, and we should therefore reject, right? Because here we know it's not infinite, and here if it's not infinite, we've already proven that there also aren't unique paths for each string, which means that the number of strings in the language couldn't possibly be at least 3. So now in these 2 steps, we've created a decider that decides 3 DFA, and that would be the answer to that problem.